It's my pleasure to talk to you today. We heard this nice economic theory before. I will concentrate on somewhat of the opposite because I'm neither an economist, I was a physicist, and neither a theorist. I was experimental physicist, which experimental physicists are in conflict with theories. They try to avoid theory, just hard data, and whatever people can make of it is another matter. So still, I will try to bring out some of these absolute truths that we find in natural laws as formulated by scientists in the service of business people for practical matters. Many of my ex-colleagues may consider me a traitor for having abandoned the academic research ivory towers, but I felt that was my calling. So what I mean about natural laws is many aspects, particularly growth in competition, survival of the fittest, this Darwinian type of competition, homeostasis, equilibrium, life cycles, chaos, complexity, all these things here. In a way, most of these things can be brought back to the very fundamental law of growth in competition. And what is growth in competition is the way rabbits grow. When you put a pair of rabbits in a fenced-off grass field, they will multiply, and they will multiply. The population will grow exponentially in the beginning, like an explosion. But then later on, as it reaches the capacity of the field to feed a certain number of rabbits, the population will start to reach a ceiling. In fact, it may even oscillate around the ceiling as there is an equilibrium between more rabbits coming and not enough grass, and then rabbits dying away and more grass growing. So there is this kind of homeostatic symbiosis of the grass and the rabbits. But the particular pattern is an S-shaped pattern. And that is the so-called logistic growth, or what I like to call S-curve growth, because it's like an S-shaped pattern. It has a very rigorous mathematical law behind it, and we'll talk about it in the most detail. But when I left academia, I went straight into a computer company, and when I started talking to them about rabbits, they kept telling me, what have computers and rabbits in common? Why are you talking to us about rabbits? And I found this joke which I like, which is they can multiply. But in fact, I added the little caveat that they do it in exactly the same way. We saw how rabbits multiply, and here's how computers multiply. This is the first computer I tried, which turned out to be a textbook case. It was the then very successful, famous Microvax, mini computer, one of the early mini computers. The VAX 11750, and when I came into it was up to it was a middle of '85, and I took the cumulative data. I took the data of those sales Europe-wise, and I said, is this possibly behaving like a species, filling a niche? So if that's the case, you should follow an S-shaped pattern. And when I put the cumulative sales down, you see this histogram, I found that it indeed looked very much like an S-curve. And then when I did fit the S-curve mathematically, I was able to expand it, to project it in the future and make a forecast, and then deduce also, because this is cumulative, deduce the life cycle, which is the rate of sales. If you want, this graph is deduced from this one by successive subtractions. This point minus this point is this point. And this point minus this point, this big step is this one. So you see, you can go from one to the other, either by adding up what you have up to then, or by subtracting successively from the cumulative curve. So this is the life cycle of a product, where something marketers are very familiar with. My surprise was that the famous product was phasing out already, because we were right here. So I rushed to the marketeers of that digital equipment, and I told them, are you aware that your cash cow is phasing out? They didn't want to hear anything about it, particularly from a physicist. They say, you're not aware of the facts that we have a midlife kicker. We're going to throw in the software for free. We're going to advertise. These points here are seasonality. This is a summer quarter where people don't buy computers because they go on vacation. And this lifetime will be as long as the previous product, that is 15 or 20 years they were expecting it to be. I said, fine, let's sit and wait. Because if there's any value to this approach of relying on laws, is that they are invariant over time. That is, you can project them into the future. It's long-term forecasting that is useful, even if it's imprecise, rather than the near future. So 3 years later, the data came in, as you see, the red line, and it is in very good agreement for a 3-year loan forecast. And then I went back this time to the same marketing department and find out whatever marketeers are still left in the company, because the company was feeling the squeeze by now. It was heavily based on this product. And I said, what's the matter? Didn't you advertise? Didn't you throw in your kicks? And they said, we did everything, but we made a big mistake. We brought the follow-up product, the Microvax, which was the same performance for a third of the price. And we cannibalized our own market base. And I say, well, when did Microvax come in? It was announced in early '86. It started selling in mid-'86. So by this time, this product was well on its phasing out trajectory. In fact, you bought up Microvax right at the right time. But the product had its destiny sealed somehow by its genetic characteristics. It had the capacity, the price, and the niche it was filling, which was for that particular product. Microvax had another niche to fill, and if they hadn't brought it at the right time, which is just about the right time, when this is phasing out, what I call the fall season of the life cycle, they would have lost customers to competitors. But it's not only computers. I realized that many other things, many other products and entities which grow under competitive dynamics follow this S-shaped pattern. And here is US cars, the registrations in the US car cities in America, which the car came out sometime in the early century, and then it populated the roads and the space, society, in a way that is a natural, a competitive way. The competition there is against space to park or other cars, or all things included. It's a natural growth process. There's a deviation here around the war, and it's understandable because that's a non-natural phenomenon. And the niche is roughly filled. By now, I'm sure it's, and I expect it, again, as it reaches up here, to go into some auto-regulatory mechanism to, it's like the rabbits occupying the ecological niche. A more intricate, because variable that you can try to track, is car accidents. You can think of accidents as species that's growing into a niche permitted by society. Because society, if it wants, it can eliminate car accidents completely by abolishing cars. So, but that is not desirable. So society allows the car to come with whatever bad aspects it brings along, accidents in one of them. These are deadly accidents. And of course, the deaths come up and they grow. They grow in a natural pattern. And oddly enough, they saturate it and they start oscillating like rabbits at a homeostatic, I call it in quotation mark, homeostatic level of about 23 or so deaths per 100,000 per year. I'm normalizing the population because society feels the pinch. If society wants to, it goes back and then clamps this down. But this level is, the homeostasis carries a connotation of well-being. That's not only what society tolerates, it's almost a desirable level, because if you drop it here by enforcing whatever laws, you may, it's not going to pay elsewhere. You're going to lose value of use of this car elsewhere. So when you find that a natural curve, a natural growth curve reaches its ceiling and then oscillates there, even with diminishing amplitude, this level here becomes an invariant because it's very easy to forecast, first of all. It doesn't change. It will oscillate, but it will not change. And it's invariant because if you go track it down, it's the same in all societies and all times. So with a few exceptions that are maybe not worth to go into now, grossly becomes what physicists call invariant. There are many other invariants in life. You have to be sometimes more clever to detect them. For example, I'll go fast through them just because they give some insights. People are happy when they're on the move every day for about 70 minutes. No more, no less. This is the homeostatic well-being. Prisoners who are confined to a cell will pace up and down to get their quota, and people who travel too much, commute 1 hour in the morning, 1 hour in the evening, they reject it. They don't want to be aware they commute. They play games, they watch movies on airplanes. More than 70 minutes per day is not, that's the optimum. Also, on this traveling time, the quota that people spend is 15% of their income. Income is the sociobiological equivalent of energy. So an organism that displaces itself for 70 minutes spends about 15% of its energy in displacement. One thing that you all are familiar with is the sleep work. 8 hours sleep, 8 hours work. This is also an invariant across countries and across time. An intriguing one is mammal heartbeats. It appears that all mammals, when they die, their heartbeat has accumulated 1 billion heartbeats, grosso modo. Small mammals like rabbits, like mice, have a very high rate. They die young. Elephants have their heartbeat going at a slow rate. They die old. So humans confined to this invariant for hundreds of thousands of years until the turn of the 20th century, when this went down because mostly of improvements in human mortality. Human mortality was reduced on the beginning of the 20th century. But at the same time, what was increased was accessibility to legal abortions and prenatal deaths. So that if you take the life expectancy at conception as opposed to at birth, the invariant pretty much holds still. But we're veering away from... there are other invariants. I'm not going to spend time. Many of them, some may be familiar, some may be surprising. Some doctors told me that they couldn't beat infections, in-hospital infections, below the 14% level, no matter how hard they tried. And then after my presentation, they start thinking that maybe this is a homeostatic level, and we shouldn't spend any more energy and effort to go beyond that, considering that hospitals have to have treatment for all diseases. Therefore, some germs and microbes will circulate in the hospital by necessity, and so on. If you look at the real data, here's the annual mileage of cars. It hasn't changed over 60, 70 years, except again for this period of the war. And war, again, comes here as a non-natural cause. Now, the S-curve we'll be talking about has a law. I'm not going to give you the mathematics, but I will tell you in words what it does. It says that the rate of growth is proportional to two things. Independently, it's proportional to the growth already achieved, and also at the same time to the growth remaining to be achieved. Growth remaining to be achieved implies a cap. There's a limit. You cannot grow infinitely. There's always a final ceiling where growth will flatten. So that, but what's interesting is also the other aspect, which is that it's proportional to how much has already been achieved. It's the same equation they use in epidemiology, in the spreading of epidemic diseases. That is, you have the rate of the spreading of an epidemic is proportional to how many people have it and how many people do not have it. In the beginning, that only 1 or 2 persons have it, the rate of growth is very low. In the end, when everybody has the bug and there's no more people to be infected, again, the rate of growth is low. In the middle, where half the people are sick and half the people are healthy, the rate of spreading is maximum. So But this curve has been used also by psychologists, by biologists, ecologists. It's a popular curve. It's called a learning curve. From that point of view, it's very interesting that learning is proportional to how much has been achieved already, and also how much remains to be achieved. Remains to be achieved is you cannot learn forever, and how much has been achieved already is you cannot learn without a teacher. You know, you cannot start from zero. It's like the famous proverb, like most proverbs, also contain a grain of absolute truth. The proverb that says, you cannot make gold without gold. If you don't have nothing, you cannot start growing under natural circumstances. So also, it is very similar to the Gaussian, to the normal distribution, the so-called Gaussian. It's an artifact, it's a mathematical concoction, not based on a law. Gauss was the prince of mathematics. But the two are practically interchangeable. You see the two curves here. So I stick to the life cycle rather than to the normal, just because I know there is a law behind it and I can feel more comfortable using it. To point out that in the very early stages of the S-curve, it's indistinguishable from an exponential. And so is the life cycle. In the beginning, these curves are asymptotic. They go from minus infinity to plus infinity. So at the very early times, you cannot distinguish between exponential, S, or bell-shaped curve. So from that point of view, if you have very little data, your curve could be this one or could be this one, and you have no way of telling if you are looking only there. In fact, it's a big decision to make whether you're going to look at an S or at the life cycle phenomenon. But we'll see both of them here. This requires some experience. Let me give you a success story. When my book first came out in 1992, AIDS was menacing society, and some alarmists were arguing about the threat to the human species because it was galloping as an epidemic and there was no drug for it. So I wonder whether it was a species growing into a niche of its own. To approach that, I normalized to percentage of all deaths because I knew the society has a thing about the number of people that die every year. So it turns out that I forecasted something like 2% of total number of deaths. And the way it came out, it was exactly limited because by now, the total number, this is the cumulative number, the total number, no, this is the 8 victims. The total number of victims in America has been in fact going down. This number started oscillating with big oscillations, but we're more down to declining now than continuing. So to me, this was like being able to see behind corners. You see something that's growing, and naive forecasters may put a straight line, or more sophisticated will put an exponential, and they will be both wrong, because what it does, the rate of growth is, as I said, the derivative of this graph. So it goes up and down, and by seeing something going up, we predict something that will go down, and indeed, it goes down in the future. As I say, this was one of my success stories, and I'd like to bring it up. But you can think of, you can generalize the concept of competition. You can say, as accidents, as criminals have careers, in quotation mark, that are growing natural because they also under competition, particularly with the police. And here is, if you measure criminal careers in terms of the victims, here is the famous Red Brigade in the Italian back in the 80s and the 90s. You see that the band was disbanded when it was practically completed. The work of this group was almost finished when the police killed it. Alternatively, you can say the police was able to cramp down on it because they were about to finish. Then they didn't have much more life to them, so to speak. I will generalize a little more. Here, the number of victims killed in Vietnam. So Vietnam, see the agreement between the purple line, which is the theoretical S-curve, and the actual people, actual US soldiers died in Vietnam, is excellent, and shows that there was a natural process there that began and finished completely with no deviations whatsoever. The question rising is, do all wars go like this, or is Iraq the same thing? And here's the data on Iraq. And here what we see is that there is a good agreement between S-curve. I updated this just before we came here. This has been updated including February. So that in February of 2009, the curve is 88% complete. But the end of the curve, theoretical end is in infinity, it's asymptotic, but the nominal end, let's say the 99% level, is around 2013, not next year, as Mr. Obama says. Of course, there will be fluctuations, but no, I mean you can expect deviations from the curve towards the very end. What's interesting here is the beginning of the curve, because you see, to get a fit here, I had to allow for early missing data. So I backcasted the curve. I mean, once you have a mathematical description of a curve, you can go back and forth in time as far as you want. So I estimated the beginning of the Iraq adventure, if you want to call it, back in 1999, the 1% level. And then I want to see what happened in 1999. And indeed, I found something very interesting. I found that in late April of 1999, the United States Central Command, led by Marine General Zinni, conducted a series of war games known as Desert Crossing to assess potential outcomes of an invasion of Iraq aimed at unseating Saddam Hussein. This became available recently with the liberation of the act of making public the documents. What I haven't put here, which I read on the document, is that the recommendation they came up with was is something to be avoided at any cost, unless sur absolute threat of being bombed by atomic bombs from them in American soil, and should never been undertaken with less than 400,000 soldiers at a time. But that was ignored, of course. Still, it gives an element, it gives some credence to a beginning of an Iraq activity around the time the curve points to. Now let's get to more practical matters about that may have an impact on the crisis and the price of oil. Here are two curves which I've constructed. By the way, much of my work is inspired by Cesare Marchetti. Professor Malik already mentioned him to this morning. So that's how I was introduced to the subject, and then I've been carrying on ever since. So here is two graphs. One is US crude oil production, and the other one is US discovery of reserves, proven reserves. The green line is the proven reserves, and you see it's more erratic because searching and finding is a stochastic process. Sometimes you find, sometimes you don't find. There's a little jump and so on. But by and large, the curve and the data are in good agreement by any standard. Even better agreement is the production. The production of data are indistinguishable from the theoretical curve up to a level which is almost the top. Now notice how parallel those lines are. There were about 12 years here, 12 years here, 12 years here, 12 years apart. That means you discover what you're going to produce 12 years before you discover it, no more, no less. That means it's the production that stimulates the discovery. You can always go discover more if you dig deeper and faster, but it's uneconomical. You don't want to spend money for no reason. And that, nobody put this regulation there top down. It's a bottom up, it's an observation, but that's how it works in America. Interestingly, as you go up here, this distance becomes bigger and bigger, and in fact from here on, there's a gap here. There's a gap of about 22 billion barrels that will be proven at the end, proven reserves that will never be exploited in America for other reasons. I mean, even now, there's crisis. These data are updated. There were crises about oil price and embargoes and everything else going on, and these curves didn't budge. There were crises here in the 80s. There were crises because they are controlled by more fundamental forces and needs. And as long as there is available oil coming into America from offshore or from elsewhere, they're not going to bother digging deeper, farther with more expensive ways to get their own oil. In fact, the prediction here is, as I say, there will be 22 billion barrels of oil left untouched in America. That doesn't surprise me at all, as we see later on from the point of view of energy consumption and different energy sources that will be coming into play. Here is the life cycle curve. Huh? This is exactly the curve that corresponds to this one here, to the brown points. That's cumulative, and this is the rate per year, yearly, monthly. It's a monthly rate. Look how good agreement. This is not a fit here. I didn't fit the yellow line to the data. I fitted the yellow line to the brown data here. And then I make successive subtractions to get the yellow and this is the real monthly data. And the agreement is excellent, and we're really phasing out on oil in production of oil in the US. As I say, basically because there are other sources coming in. So if I can just make a cap, to cap a few of the things we said so far, society has auto-regulating capabilities that can be detected and projected. That's where the forecasting comes in. Projected into the future, you're not going to be able to see when a dip or spike will be, but you'll be able to see how it will be 5, 10, 20 years from now. Well-established natural growth patterns, the so-called S-curves, are indicators of an optimal course, the least resistance pattern. Just like the ceiling of the S-curve is a homeostatic well-being, so is all the path going there. Going faster or slower will be counterproductive, will be against the minimum resistance. And then a new course can be set before the growth phase, because once you are in a well-defined growth pattern, trying to avoid it will be self-defeating. You can try to change the direction when the curve is either not started yet or it's completely finished. So the rhetorical question is, where are you on the curve? And my practice is based on what to do about it afterwards. But can we now use S-curves to look at the economic turnaround? That's the burning question that everybody's been asking. I will look at 3 economic monitoring variables, even though I don't like dealing with anything that has a dollar or anything that represents a price is unreliable. Price is speculative. Doesn't represent lasting value. If you compare, if you look at precious paintings or Van Gogh's work, the works he made were worthless in the beginning, and now they're worth a fortune. Nothing changed. The beauty, the work, the canvas, the paint, non-physical variable has changed. Beauty is not physical, but it's more objective than price. And yet the price has been multiplied. So prices don't obey laws of physics. They don't obey competitive. It's not a competitive variable, price. It's not a limited resource. You cannot, if somebody takes a price, it doesn't mean that somebody else cannot have the same price, because, but if somebody takes your food, then that's a limited resource. So I will look again on the traditional things people look when they look at the economy, GDP, employment, and interest rates in America, macroscopically, and try to use S-curves to extract some conclusions for the future. So here is the US GDP from the Depression times. I notice I make constant dollars. That's my feeble attempt to get away from prices and dollars by deflating. At least I say that we're talking about something that has the same value, perhaps, year to year. So it's closer to a physical variable, so I can fit an S-curve. Obviously, it is the very early stages. It's only 29% penetration, so the curve will go somewhere, off my screen here. So it's not interesting, the curve itself, but what's interesting is the small deviations around the curve. So I take the ratio data to curve, to theory, and I find this oscillatory pattern. And now, of course, we are below. That's why the difficulties. So I try to see similarities, like the distance between troughs here and the distance between peaks, and try to get an average to see when the next trough and the next peak will be. And playing this game, I find that from peak to trough and from trough to trough, I can have 2 estimates for the next rock bottom of this variable. One is the second quarter of 2009, and the other one is the fourth quarter of 2011. It's a big disparity here, but let's keep this as one indication. We do the same thing with employment. This is the employment population ratio, how many of the people are populated percentage-wise. And again, we're speaking roughly to the same period. This is the big growth phase of America after the war. So here, it's very oscillatory, almost regularly oscillatory. And again, we are down here. We are way below the curve. I play the same game, take the ratio of data to a curve. The purple line here is a moving average of 12 because it's a monthly data. So to guide the eye, I get this moving average. But one way or another, I can play my game again to figure out when this next dip will be. I take these distances and average them out, a very naive approach, but it gives me two estimates from peak to trough or from trough to trough. I find that the bottom of this variable should be more closer to August 9 or August 10. Again, a certain disparity. Now we have 4 measurements. We play once more this same game with interest rates. We saw the interest rates this morning, the same graph. When I was looking at your graph this morning, all I was thinking of is the overall pattern. I'm talking about, long-term history, long-term future. So again, the period after the war, you see, there is a bell-shaped curve here. Bell-shaped means there's an S-curve somewhere, of which this is the derivative. So in fact, yes, there is. If you accumulate these numbers, I can fit an S-curve there, and then that is the curve I will concentrate on, trying to take the ratio of data to mathematical expression, and I get this kind of regulatory ups and downs. Again, we are down. We are down in every of these variables, and that's not surprising. And now we get 2 more estimates, and this time they both agree. They are July 09. So if I might combine all these things, we have 6 estimates for where, from GDP, from employment population, and from interest rates, the rock bottom are these 6 numbers, and I just naively take the average of those, and the average deviation gives me an estimate for the rock bottom of the crisis to be 2010, February 2010, plus or minus 7 months. Nothing exciting about the answer because many people say the same things. It's more interesting that it came by such a different way than other people get it. Okay, let's go on now into substitutions. Substitutions is a clearly competitive thing. The new replaces the old under the law of survival of the fittest. To the extent the new has a competitive advantage, it replaces the old. And this happened with cars when they replaced horses in the last 150 years. In the beginning, all transport was done by horses. Then the cars came in. These are absolute numbers here. I have a logarithmic scale because the numbers grew so fast that as the number of horses increased, the number of cars increased, the number of horses decreased, and this is the period of substitution here between the appearance of the car and 1930, basically, because from then onwards, so if you look at these numbers, there's no S-curve anywhere. It doesn't look like anybody can make a sense out of them. But if you take market shares, you say this is the total number, I'll take the share of cars and the share of horses at any given time, you find some beautiful S-curves coming. The market shares of horses declined, the market share of cars increased, and there was one-to-one substitution. The sum is 100% by definition because the market shares. And they cross sometime between around 1915. At the end, there's a few horses left, and not all cars have taken over, but this could be horses for pleasure and not necessarily for transport. No, it must be horses for transport, but very little. The interesting thing about this graph is the regularity of the agreement between the mathematical pattern and the data, because there is a world war going on here. World war shakes, they have a lot of demand on transport. But this demand obeyed We didn't feel the award on this view because this was much more fundamental. This was based on the genetic competitive advantage of cars over horses. And the replacement was going on independently of what the war was dictating. If the war needed transport in the early days, they would take half and half maybe, horses and cars. But if they needed more transport 5 years later, they would take 4 times more cars than horses, just because it had evolved. This kept evolving independently of what was happening on big scale. I will introduce a small transformation that makes S-curves look like straight lines, just to be able to go easier into the many competitor arena. This is the S-curve. In fact, I normalized to 100% by just dividing by the ceiling. And then if you take the population at a given time and you divide it by the remaining space, this is the maximum minus the population, how much space remains in the niche, and you plot it on a logarithmic scale, you get a straight line mathematically. So from now on, when I present to you any data, every time you see a straight line, remember, it's an S-curve on a linear scale. So, of course, this scale is non-linear now. And in fact, if you want to know what this variable is on this scale, the minus infinity, the 0 goes to minus infinity, and the 100% goes to plus infinity. It's a very non-linear scale. But it has an advantage. Here are 3 substitutions, classic. This is the so-called Fisher-Pry substitution model that became famous in the early 70s. This is margarine for butter, synthetic for natural fibers, and synthetic for natural rubber. Notice